Good morning, good afternoon, everybody. So today I have a very special presentation today, and that is a paper review on my previous master's work related to multi-spectral characterization of natural organic matter from Manitoba surface waters using HPSEC, or high performance size exclusion chromatography. So with this, I think it'd be a good idea to go over the paper, some of the main takeaways, methodology, and I actually have some images on the right that I can annotate, and it makes it much easier to explain the work. So to begin off, this work was mainly the use of something called high-performance size exclusion chromatography. So with chromatography, we're just going to zoom in here. Chromatography is sort of concerned with the separation of chemical compounds, and there's different types of chromatography columns, but all in all, what you pretty much have is you have some sort of sample that you're passing through one side of the column, and you're passing it through something called a stationary phase, and that's just because it's stationary in the column. And then your sample leaves on the other end, and your sample is called the mobile phase because it's mobile through the stationary phase. And depending on what your column is focused on, you can separate compounds based on their ionic charge, their chirality, or their size. So depending on what your application is, you might want to have different types of stationary phase columns for your purpose. What I mean by that is, depending on what the stationary phase is, if you have you're looking to separate compounds based on polarity, well, you'd have a sort of a largely positive or largely negative charge column, so that when you pass compounds through, they sort of get attracted by the stationary phase, and then they elute out of the column at different times. So for that reason, depending on what you have in the stationary column and your sample, and what your column stationary phase is, you can separate compounds based on different properties. So in this work, we focused on size exclusion chromatography, and here's this infographic from the paper here, where so we still have the same sort of setup where we have samples coming in the column and sample coming out of the column, but our stationary phase here is a porous media. And this porous media has a certain porous size that when you pass a sample through, your sample has many different, well, at least in this example, we'll just go with the example here. We have three different standards: PSS 15K, PSS 5K, and PSS 8K, referring to Daltons. So depending on what your sample is, and you're passing through the stationary phase, and depending on the stationary phase porosity and the size of those pores, when you pass your sample through, what you'll find is that larger compounds elute sooner than smaller compounds. And that's because smaller compounds take longer to pass through the pores. And then as a function of retention time, which is when the sample is originally injected into the system, starting at 0 minutes and going to wherever you want to end, what you'll find is that compounds that are bigger will elute sooner. We can see PSS 15K here, comes out sooner. Therefore, the peak shows that it comes out first. And then we have 5K and 8K coming on afterward. So for this reason, for this purpose, we have a sample, we can pass it through this column, and then we have a size distribution of what its composition is. So going just right here on the right here, what we also want to do is we want to characterize exactly what's coming out here. So we have standards, so we sort of know what the size of this and that is. But we also have a detector at the end of the column, where if we wanted to find out exactly what compounds we're working with, we have an absorbance detector, in this case a photodiode array detector, that can look at, for variance absorbance values, what wavelengths are your compounds absorbing. And this is useful because we can characterize compounds just like in first year undergrad courses, where depending on what wavelengths they're absorbing, we can sort of characterize them as largely aromatic or substitute in this way or that way. So for our purpose, which is the water samples, treatment with water samples, treating water samples, we would have something like a raw compound, which because it has various different sizes, it's sort of large distribution. When we treat it with a certain type of treatment, in this case, we use ion exchange. That's what treated is here. What you'll find is that there's a marketable decrease in this peak. And of course, this time, whenever you want to think of time, you also want to think of it as size, because this is size exclusion chromatography. So as a function of size, we can sort of say, hey, with this treatment, we're targeting compounds of this size, and based on the absorbance value, which like I had said was 254, we're targeting compounds that are mainly aromatic. We're sort of making a lot of assumptions because absorbances are only really good at looking at specific compounds. Like in undergrad lab, you're sort of looking at, okay, we have a sample of this, and what's the decrease? But in real life, we have compounds of various absorbances. And when they're substituted, they sort of absorb light at different wavelengths. But when we have a photodiode array detector, we can look at absorbances of various wavelengths. Oh, sorry, I should say of wavelengths is down here. Of various wavelengths. And then we can look at the absorbance value as how much light it's absorbing as a function of time, like I said, which is also size. Okay. So for this reason, we sort of have a 3D characterization of our water based on time, which is size, wavelength, and how much light it's absorbing. And because of this, we can sort of characterize the water samples and say, well, based on all these properties, we can sort of make the assumption that the compound sort of looks like this. So with that, just one last thing with regards to the photodiode array detector. This isn't that interesting, but just for the sake, I just wanted to mention that we still have the column down here with the size exclusion chromatography. That's what we're working with here. That's SEC. And then what happens is when we have this photodiode array detector, it's actually looking at absorbances at different wavelengths. So that's what all these colors is. All these colors here are on the visible wavelength, but we also cover within the ultraviolet rate. And then the photodiode array detector just means that simultaneously we can look at the absorbances of all these wavelengths at the same time. And then we can sort of look at it with our data processor, which is our sort of like our processing. So we have a pretty good idea what size exclusion chromatography is and why we want to use it. So for the purpose of this work, the question is, what are we going to do with it? Well, the idea is that what we want to do is we want to characterize water in such a way where when we're looking at certain peaks or different sizes of compounds, if we treat the water in such a way and we decrease the height of these peaks, does that correlate with a decrease in, for example, disinfection byproducts? And what these disinfection byproducts are is when you're treating water at a water treatment plant, what you do at the end is usually UV disinfection or dose it with chlorine and leave a chlorine residual such that whenever the water goes through the supply system and reaches someone's household, there's a certain residual chlorine such that at the end point, the customer, which is the consumer, is consuming water that's disinfected. So you need to make sure that there's a residual chlorine. And this residual chlorine, because it's so reactive, because it's sodium hypochlorite, what you tend to find is that it reacts with the aromatics in the water and it forms these byproducts that are carcinogenic. So for all this reason, we want to characterize several Manitoba surface waters. And in this work, we actually looked at 7. And we're using it with this technique, which is the high performance size exclusion chromatography. So great. So we'll just go into it. I'm going to skip the abstract because I want to go with it as I go on. One of the things I was mentioning about the disinfection byproducts, so I mentioned here sort of in this section of the paper, disinfection byproducts. They're known to be heavily monitored carcinogenic byproducts, and the dominant species of concern equals trihalomethanes. They're called trihalomethanes because they're methylated products, and they usually have 3 halogens attached to it, whether it be 3 chlorines to form chloroform, 3 bromines to form bromoform, or any sort of way in between, like dichlorobromo or dibromochloro, as an example. And this is just to say that there's also this other form called haloacetic acids, which are monitored by the provincial government as well. And it's formed by a very complex reaction pathway. So just because we're treating raw water, the compounds in raw water aren't very well characterized because we don't exactly know what they look like, and they differ based on time of day and based on source. So all we can do is very generally characterize them in different ways, and that's a big concern when we're focused on water treatment, is how can we best characterize water. So we're going down here. This is just to say that in the study of natural organic matter behavior, natural organic matter just refers to all the substitutes, all the compounds in the water that are natural in origin. And the thing is, so they're very carbon-based, nitrogen-based, oxygen-based, mainly aromatic carbons. And what we find is that these aromatic carbons are very reactive. And that's why it says via reaction. That's why it sort of says in a very via complex reaction pathway. It's because when you're working with these compounds that aren't very well characterized, and you're treating with chlorine, and then you have so many things going on, it's very hard to know exactly what's going to happen in the future. So we use these surrogate forms of analysis. So natural organic matter, like I said, is just these carbon-based aromatic compounds, again, not very well characterized. But one thing we do is we look at their aromaticity, and that's just because when you have aromatics, you have a lot of conjugation, and therefore, when it comes to the reaction pathway with the chlorine and the natural organic matter, what you find is that when things tend to be more aromatic, they're more likely to react. And again, this is sort of very generally speaking. And of course, people have looked at different absorbance. So whenever you say UVA 254, that's actually referring to absorbance at 254. 272, as an example, trihalomethane formation. So people are just looking at, hey, if my sample absorbs light at a certain wavelength, can I say something about the formation of these trihalomethanes that we know are carcinogenic? So as a result, there's all these surrogate measurements that we can use, and that's just because they're very easy to do at the endpoint when you're a water treatment operator. You can measure it on a daily or 4 times a day basis. I think they do it twice a day. But the question is, from the research perspective, is can we do a little bit better where we can use something like high performance size exclusion chromatography? And can we look at a multi-spectral apparent molecular weight? And it's called apparent molecular weight because it's not very well characterized, even the size. So we say, very generally speaking, approximately what are these apparent molecular weights? And could we correlate that with the formation of disinfection byproducts? And this is just another thing saying various different apparent molecular ranges have been tied to formation, reacting with natural organic matter. And humic substances are a subset of natural organic matter that are known to be the most highly reactive. So the ones, humic substances are what we're most focused on from a research perspective. And if you ever wanted to know what humic substances actually are, if you ever look at a lake and you see greenish, brownish color, that's humic substances, and that's just decaying plant matter. Yeah, so we're sort of correlating certain apparent molecular ranges, which is the important part. Ooh, go back there. And certain apparent molecular ranges, which relate to apparent molecular ranges in the chromatogram. So the other thing we wanted to look at in the paper was, so we wanted to see, okay, if we target certain peaks of our HPSEC, so going back here, if we targeted certain peaks, different sizes of different wavelengths, first of all, how do we sort of treat the water in the first place? And one thing that we did was ion exchange, was a big part of my master's research, was looking at the effects of ion exchange, because at the time it was known to be one of the leading, when it comes to closed base contactor tanks, one of the best forms of treatment for humic substances. And how these sort of work is, it's pretty much an ion exchange, so it's performing ionic exchange with the water. So similar to how you have a chromatography column and you have a fixed bed, you'd have what you would normally have as, let's just say, a water softener tank. You would have an ionic exchange resin tank. And what you'd have as a resin inside these tanks are these different resins. And attached to these resins are certain compounds. So here's a strong acid cation, strong basic, weak base, and weak cation. And all you need to know is that the whole purpose of these strong base cation resins, these are the ones I want everybody, I sort of want to focus on, is that, oops, I'm back again. Remember not to do that. Is that these polystyrene resins, they sort of have this aromatic backbone, and then depending on if it's a type 1 or type 2, you sort of have this substitution here. And this matters because we want to treat water because it's ion exchange. So we want to exchange this Cl minus with an acidic group attached to the humic substances. And that's because when it comes to these humic substances, what we notice is that a lot of them are things like carboxylic acids. So if we know that the humic substances exist and they're mainly characterized by, let's say, absorbing at 254, and we know that they are mainly acidics, what we can do is we can set up a resin where when we pass our water through these resins, this Cl minus can form with the H plus and the acidic groups and actually exchange. Let me just erase it here. Okay. So we sort of have our water flowing through, and then we sort of have these like I said, these carboxylic acid groups. So let's see, OOH. Right? And then what happens is this H will form with the HCl, and then the O will sort of replace to the resin. And what happens is when the water passes through a series of these resins, what happens is all these carboxylic acid groups attach to these resins, and then the water that passes through is free of is free of the acidic groups, and therefore it's a form of treatment. And depending on whether you have a strong base or a weak base, all they do is they change the substitution here, and they change the substitution based off of whether or not these terminal groups are electron donating or electron donators, electron withdrawing. So for example, this OH minus here is very electron withdrawing, so it's going to draw electrons away from this, I think that's an amine group, right? So it's going to make this sort of bond here. So it's going to make this bond here very weak, very likely to break and exchange with something that's passing through the column. As opposed to here, we have something like just a methyl group here. This is electron donating. So rather than drawing electron charge away from the amine group, what it's doing is actually donating to this amine. And as a result, this bond is a little stronger, so then the Cl is less likely to exchange with compounds, right? So depending on how strong the base is, it sort of tells you if you're going to exchange weak or strong acids from the sample they're passing through the resin. So very interesting stuff, and this sort of figure on the right here is sort of saying something very similar. And down here, I sort of have this, which was from one of my other papers, and this has to do with sort of, again, characterizing natural organic matter as a function of parent molecular weight. So depending on what paper, these are all different papers here, which in my other paper, I sort of have the references for these. So depending on what paper you look at, the authors sort of suggest, hey, if I'm looking for humics, which are humic substances, again, which are these highly aromatic, high precursors to disinfection byproducts, if I'm focused on humics, approximately what size am I looking at? What range? And depending on the paper you're looking at, they sort of have different ideas for what they think is the appropriate range. But what you tend to see is something within 10 to the 3 and 10 to the 4, so 1,000 to 10,000. And of course, there's lower molecular weight acids. So those lower molecular weights maybe perhaps are stronger acids. So they're more likely to be replaced by a strong base type 2. And maybe these bigger ones are bigger. You know, their charge is more evenly distributed around a large hydrated radius. And therefore, you maybe need a very strong base, like a base type 2, in order to remove them. So there's all these characterizations. It's very difficult to pinpoint exactly what's going on in the water. We sort of do our best with what we can. And of course, there's these other things like building blocks and polymers. So again, this is sort of a nice little infographic just summarizing all that. Let's see if I can get back to where I was here. So just as the summary for what we're trying to do, we hope to characterize the removal of natural organic matter. And we did this following strong base ion exchange application, which I sort of explained here. And we looked at 7 Manitoba surface waters, and then we used a multi-wavelength size exclusion chromatography. We looked at various wavelengths, and we were trying to see, hey, if we remove this peak, which is this size, and absorbs at this wavelength, does that correspond to a removal of disinfection byproducts? And if we did find that correlation, then we can sort of say, going forward, if we target this specific apparent molecular weight, we can do it through, we can use it through a membrane or whether through another ion exchange column, whatever it may be. We can therefore make better predictions about the removal of these carcinogenic byproducts. So with that, the materials and methods goes a little bit more into exactly the specifications of the column, the ion exchange absorption, of how we sort of dosed it. There's a lot of considerations that is sort of beyond the scope of at least this presentation. And then this sort of little image, which used to be there, image here, just serves to demonstrate that when we're looking at all these different source waters from Stanford, Rainy River, Pine Creek, all these different areas of within Manitoba, what we found was when we contacted it with ion exchange resin, what you notice is that mainly a lot of these peaks here actually disappeared. Actually, no, I think this is sort of the original. Let me see, as the chromophoric then, actually come to think of it, this is actually the original water sample. So this is just to demonstrate, now I sort of remember, that when we're looking at these 7 different source waters, there's actually a lot of distribution when it comes to what sort of compounds you're looking at. So there is these huge peaks that we found just south of 10 to the 3, so it could be in the 800, 750 apparent molecular weight, which again, going back up here, we can say what sort of, we can sort of say, okay, what's around 730, 800? Well, we tend to see low molecular weight acids, right? And perhaps some humic substances. And then going down here, jumped again. And then going down here, we tend to see these large peaks found at, that could be at 20,000, 30,000 Daltons. Well, what's found at 20,000 to 30,000 Daltons? Well, we sort of have these lower but large humic substances here. So that's where you find this. So this is sort of how this sort of illustration is looked at here. Other thing to consider of why we were sort of concerned with why this illustration is important is because we wanted to actually look at these peaks in their entirety. So we wanted to say, hey, you know what? We notice that there's these large peaks between 0.6 and 1.1 K Daltons. So we'll call that peak A. And depending on what happens to peak A, we'll look at sort of the whole area under the curve here. We'll integrate this curve and we'll sort of say what happens to this peak when we treat it. And does that correspond to disinfection byproduct formation? And then we also notice that there's these two sort of humps here. So we sort of refer to these as peak B and peak C, and within these ranges. The other thing to consider is that this has to do with sort of absorbance, and why it's so difficult to characterize is because we have something like a benzene, and we know for a fact that I think benzene absorbs light very well at 254 nanometers, but depending on the substitution, and also depending on whether or not you have one or more aromatics which add to the conjugation, what you find is that benzene absorbs light really well at 254, let's just say, but when you have more of these aromatics, it actually pushes the absorbance spectrum down closer to 350. So if we want to capture a lot of this information about these extended conjugated aromatics, what you want to do is you want to look at various wavelengths, because once they're also substituted with different groups like carboxylic acid, aldehydes, and alcohols, what you'll find is that these absorbance spectra also shift right to left. So we want to characterize it all. So we want to capture the full extent of this nanometer range. And I think for this work, we started at 210 nanometers. So we started at 210. And I think we went as far as about like 380 or 360. I'll just write 360 for the sake of argument. So we captured the visible and ultraviolet wavelength range. The other thing to consider about when we're looking at size and why we're looking at apparent molecular weight, like why is it called apparent, is because there's no way that we could actually capture the compound. Like as an example, we can sort of find exactly what the size of this compound is by just counting the number of carbons, the hydrogens, and the oxygens, and counting, okay, exactly what would be the size of this. But in reality, when we're working in aqueous environments, we have compounds of different sizes, and they're complex with different things. And complexation just means that when you have a compound that exists in an aqueous phase, it's within a solvent, and that solvent sort of forms a barrier around the compound. So for an example right here, I have something called ion and solvent effects. And that just means that we have this positive, this could be our humic substance, and we have all these H2O atoms around it, and it's complex, meaning it's sort of considered and it's treated almost as if it's a single compound. And there's no way you can separate the water from that ion. So it's part of its what's called hydrated radius, which is its radius when it's sort of hydrated with water. And of course, there's different compounds in the water that are sharing the same H2O molecule. So this just goes to show like why it's refers to as Foss effects, I believe, is that when we're doing the characterization and the standardization, we sort of treat compounds not as if they're just single compounds, but as if they're distributions. And that's very important because when we're sort of characterizing even the standards themselves sort of have this distribution with tails. And these tails are just because there's compounds within the standard that appear slightly bigger and slightly smaller. And that's also because it's sort of like when a sample is injected in the chromatography column, there's that slow separation over time, and these sort of develop tails. But also because within the standard, it's also reacting with the mobile phase, which was a phosphate buffer. And the Foss effects was just one other consideration that we had accounted for, which is when we control for the ionic strength in the mobile phase, what you find is that you could limit these effects, and therefore you have a better characterization of your size. So that's all this Foss effects was. So now going here a little bit into our forms of characterization. So going to go reset there and go back here. I'm going to jump right to the correlation coefficients. Was our way of saying if we decrease the heights of these peaks, how can we say for certain, or at least with a certain probability, that it correlated with a reduction disinfection byproduct? So where do we get those correlation coefficients, or what correlation coefficients can we use to relate the decrease in the integration of the curve, which is the height of those peaks, with disinfection byproducts. And the thing that we had done was we used two things. We used Spearman correlation coefficients, which is very common in data science, and something called the Pearson correlation coefficient. So what these Pearson and Spearmans are doing is when you have two independent variables, let's just say here we have x1, so we'll just call this x1 here, we call this x2, right? Ideally, we look at this and we sort of know that this is some form of uniform noise, and there's no correlation between x1 and x2. So ideally, we want some correlation coefficient to tell us that there exists no relationship. And the equations for those are here, but you can just sort of, just for the sake of this discussion, we can just sort of learn just from looking at it that there's no correlation coefficient. As opposed to the Pearsons are here, it will actually show, let's just dump the Spearman, because Spearman tends to be the more powerful one. It has a low value for the Spearman coefficient when the noise is random, and also when there's outliers. So the Spearman is low when there exists no correlation between independent variables and when there's outliers. Additionally, the Spearman also can account for these sort of monotonically linear trends, in which case we would say, hey, when we're looking at the decrease or the increase of this peak, we do see an increase and decrease corresponding with the formation of disinfection byproducts. Therefore, it has a high Spearman. And additionally, the Pearson's coefficient also has a high coefficient for these linear monotonically increasing values. But what you find is that the Pearson is sort of not, is very prone to outliers. So Spearman tends to be the more robust measure. And additionally, one thing that the Spearman does that's very advantageous is that a lot of these relationships aren't linear. And that's because in real life, a lot of things are complicated. Not every two variables are linearly related. So it can actually capture, a logarithmic or exponential plot as well. So if we notice that we're sort of targeting that apparent molecule, that peak A, and we're sort of decreasing it, and we see an exponential decrease, let's just say, in disinfection byproducts, well, even the Spearmans can also capture that information as well. So really interesting stuff. Down here, going to table 1, these are just the different ion exchange resins that we had tested. So these are just various different manufacturers. They're all polystyrene, quaternary amine, and that just means for every amine group, there's four groups attached. So that amine group has a positive charge, and it makes it extremely basic. There's certain capacities for exactly how many per milliliter of resin, how many milliequivalents of charge we can actually substitute off the water. And of course, there's water content, and this sort of matters a little more for manufacturing and the final application. So for the sake of argument, we're just going to skip that for now. Table 2, this was sort of a summary of, when we had compounds, what we did was we dosed it with different values of 3 and 5, and we tried to determine exactly what the molecular weight of the compound was. And the reason why this is very difficult to do is because we saw that when we're looking at samples, it's a distribution. So it's a little hard to say what is the size of this water, right? Because it's a distribution. So all you can do is use a bit of averaging, summing over averages, and then we can sort of have a general idea on, okay, this water is mainly molecular weight, apparent molecular weight size of 4,634. And this is important for us because even if we have these distributions, when we're dosing with different concentrations of the resin, what you'll find is that it targets the lower molecular weight of the spectra versus the higher molecular weight. So it's also targeting the size as well, even though it's only exchanging for the ions, right? And this is important for us because, again, it's all about characterization. So if we're removing ions, we're removing strong and weak humic substances, and we notice that when we're removing more of those charges, the molecular weight size decreases or increases here. So this goes from 4,6 to 5,5. What that tells us is we're removing a lot of the lower molecular weight compounds, leaving only higher molecular weight. And also, if we notice that the disinfection byproducts drastically decrease, well, that sort of tells us that the lower molecular weight of the distribution is mainly those that are contributing to the disinfection byproduct. So that's very interesting for us to know. These are just different measures for the different water samples, because again, these are taken from various different places within Manitoba. So we're going to go all the way down here and look at some contour plots. And this is a little bit difficult to discern, so I don't want us to focus too much on this. But this is pretty much just to say, hey, for each of these 1, 2, 3, 4, 5, 6 water samples, this is, I believe, let's see, 3 milligrams, 5 milligrams. So this is when we treated with 3 milligrams per liter of the ion exchange versus the 5. What was the, as a function of wavelength here, and this is size, again, 10 to the 3, 10 to the 4, what did the absorbance values look like? What were the height of the peaks? And this is just capturing the height of the peaks. So it's a little difficult to pick out if there's anything here, but I would just say, just for the sake of argument, that, the peaks here are a little larger than here. So when we were sort of contacting with the ion exchange resin, it seems to be that this sort of smaller peak here, which, just to go back up here, refers to this peak A. See, some samples don't have the peak A. Some samples do. What you find is that perhaps it targeted this a bit more, and not so much this. Right? So again, it's all about characterization. This is just visually looking at it. But the more interesting things that we're looking at actually are sort of these heat map plots. And this is very interesting. So this is actually looking at TTHM, total trihalomethanes, which is the summation of chloroform, bromoform. Just think about all the disinfection byproducts that we're concerned with that are carcinogenic. These are the sum of them. And these are the 3 main compounds. Okay, so this is sort of the same as this right here. And then additionally, we have things like absorbance, TOC, SUVA. For the sake of this discussion, unless you're very familiar with the way that water is treatment, I'm not going to focus too much on this because it already takes a little bit away about what we're talking about in the paper. But pretty much we wanted to look at, for these peaks. So again, here we go. We have peak A, which was that short, early, tall peak. We have these shorter but broader peaks in peak B and peak C. And then what we have is R240 to 470 to 280. So what peak A was doing in peak B and peak C was, again, just looking at those specific slices of apparent molecular ranges. So it's taking slices of these chromatograms. So for example, peak A just took a slice out of this and integrated these curves. Peak B, conversely, just took a slice of this. And peak C took a slice of this and integrated it. So then we have sort of we integrate those curves and we have a value for how pronounced those peaks are. And then we sort of said, when we decreased or increased these peaks, did it correspond to increase and decreases of these values? So these are all Pearson correlation parameters. So with Pearson correlation parameters, which I totally had forgot to say, you're looking at values that are between, if I recall, it was between -1 and 1, where when you have random noise like this, you're going to get values of 0. And when you have these positive relationships, again, linear or monotonically increasing, you have values of 1. And then when it's there's a negative relationship, you have values of -1. I think so, yeah, because these values can't be negative, so that is the case. I had to double check that. So the thing we were looking at are high values that are close to 1. And what we find is that we do see high values of here close to 1 and high values here close to 1. And what we find is those tend to be the case with CHCl3, which is chloroform. So what this tells us is when we are targeting specifically peak B, what we find is that there's a strong relationship with targeting peak B and chloroform formation. And again, this is a total trihalomethane, so it includes all 3. But if we're just looking at specifically bromoform, we see it's negative. It's sort of negative. And again, when we're talking about negatives and positives, you're only really concerned with anything above 0.6 and anything below -0.6. When we're getting closer to 0, there tends to be not so much relationship. We're getting closer to like random noise. So it's a little hard to discern, right? But values, let's just say closer above 0.6 are of interest to us. So this tells us something quite interesting. Now this is something else. We looked at R240, R272. Maybe I can get another color for that. I'll shake things up a bit. Go with blue. We have 2040, 4072, and 7265. So what this is telling us is rather than taking slices of apparent molecular weight, what we were doing instead was taking slices of these ranges here. And again, this is a 3D spectrogram, right? So there's peaks that just appear here. So that's 240 to 260. Oh, sorry, I said. So that's sort of this here. Was capturing all of this. And we can see there's a lot of tall peaks there. And then 40 to 72. So that'd be sort of this slice. And then 72 to 365, which is this larger piece. So you can see that we're actually even slicing all of the available wavelength ranges as well by sort of capturing this. And what we also find is that, again, those really didn't correspond too much with high values for the Pearson correlation coefficient. Again, we see values of close to 5.6. But again, we sort of looked at this. We sort of have a general idea. This is all for the Pearson. And again, the Pearson is the one that is kind of prone to outliers. So maybe those values aren't as pronounced as we'd like. So when we were looking at the Spearman, we actually didn't see, actually come to think of it, actually the results kind of got worse. So we do see values of 0.6. Again, nothing too much here. 0.58, right? But generally speaking, we're still seeing similar trends where we are seeing decreases or increases. Well, they're always decreases because we're actually removing compounds. Decreases in chloroform, and we tend to see it. It tends to be more, I mean, it's a little harder to say here. But definitely we saw it with peak B here, and here we saw a peak with peak C and peak D. Again, these correlation coefficients are sort of telling us different things. It's a little hard to say. But generally speaking, at least in the literature, we did find that compounds that approximately in peak B did target trihalomethane. So this did sort of correspond to things that we had found in literature previously. So yeah, a lot of interesting stuff. So the paper, just the final thing on this paper was, rather than just considering peak A, peak C, rather than just considering these three ranges, there's actually nothing that says we couldn't just consider all various combinations of different ranges. And what I mean by that is here we have something called lambda initial and lambda final. And what lambda initial and lambda final is telling us is if we were to just integrate the whole peak between 210 nanometers and 400, right, that would be this point. Okay, so if I integrated between 210 and 240 and saw if that correlated to the reduction in, let's just say, trihalomethanes, then this would appear higher. So these are Spearman correlation coefficients, and these lambda initial and lambda finals refer to the ranges that we chose. So just to be super clear, right down here, all the way down here refers to if we were to take lambda initial, which is 300, or actually I should say right here. If we were to take lambda initial at 230 nanometers and integrate the curve all the way up until 300, and we were to correlate that with trihalomethanes, would it be higher or lower? What would be the Pearson correlation coefficient? If that sort of makes sense. So I think it sort of looks really good when we actually look at these sort of results down here. And that's just because we actually see something a little more interesting. I'm going to jump right to these ones because these values are a little closer to 0.6, closer to 0.6. So I'm just going to look at this one. I'm just going to look at this one here. So again, we're concerned with values that are closer to 1. So we're looking at these dark areas, right? So this dark area is telling it that when we integrated the curve between the initial of 240 and let's just say a little earlier, let's just say 230 and 260, which would be right here. What we found was the correlation between the decrease in that integrating that curve, decrease in that curve corresponded to larger values of the Pearson correlation coefficient. So what this is in fact doing is rather than playing around with exactly what ranges and exactly what parallel molecular weight ranges, exactly what absorbance ranges look at, let's just look at all the absorbance ranges simultaneously and try to find out if there's certain slices that are more likely to correspond to, again, total trihalomethanes, which is a combination of chloroform, bromoform, and all the dichlorobromo, bromo, dichloro. So yeah, that's interesting stuff that we had come out looking at. And then we sort of saw something interesting where this is actually closer to, who knows if that could be 0.62 or something, which is quite high. And at least with chloroform here, we notice that there's this broad area, which again is between initial of 230 and 265. So this is just telling us, hey, as our sort of academic contribution is, hey, you know what? Maybe it's these particular range that we should focus on. So when you send a sample off to the water treatment, or off to the lab, and there's very pronounced high peaks within these ranges, then that should tell you something about the formation of chloroform, which is important for us to know. Again, we're characterizing the best we can. This is not really a form of quick characterization, but if there are other ways, for example, that you can really find out from 230 nanometers what the compound constituency is, like, you took the UV absorbance at just 230, at least for the water samples that we looked at, there was a reduction in chloroform. Again, characterization, looking at different ranges, very interesting stuff. Okay, so with that, that's actually the end of the paper. I hope everybody enjoyed it. I think this was a good first start of my paper review. Probably in the next video, I'm going to cover one of the literature reviews related to HPSEC, which goes a little bit more into sort of the thinking of why we chose these certain ranges and why we're concerned with HPSEC as a future form of characterization. I think that's going to be interesting. So I thank everybody for joining, and I'll see everybody next time.